Okay, I've got 4 o'clock. So we're going to talk today about sorting and searching. Today and Wednesday are kind of a two-part lecture. Today we're going to go over the fundamental algorithms that we're talking about for sorting data, lists of data in Python and searching for it. And then on Wednesday, we're going to talk about analysis of the algorithms, or what this costs, where cost is given in terms of the number of operations it takes to sort an algorithm, which can be related to the amount of time it takes, or the amount of hardware you're going to need, or the amount of money you're going to have to pay, or whatever. So we'll get to the cost on Wednesday. Today, we're going to talk about the algorithms. Project 3 is out. I'm going to talk about that just a little bit in just a minute. And then I'm going to get into the lecture because there's a lot to cover in lecture today. So I do want to get into that. I'll talk about Project 3 again some more at the end of class. And then again on Wednesday. Lab 12 is next week, not this week. So we're not going to talk about Lab 12 until next Monday's lecture. You will have that. It's a next week project. In terms of Project 3, let's see. The assignment's on GitHub. I also put it on Blackboard if you want to get it there. I said I would put the data file on GL. I haven't done that yet. I will do that. Last time, this is similar to what I gave last semester. If you looked around at that, that's all. I talked about that. I showed you some of the examples. And I talked about that. Sorry, I just clicked on the wrong button. This will take me just a minute to fix. Any rate, last semester I had them do some analysis on COVID data. Today, just to be different this semester, with the election being such a hot topic and everything, you're going to do some analysis on election results, not from this year because it's too new. But you're going to look at some historical trends in elections for the United States Senate, and you're going to try to figure out which states are turning redder and which states are turning blue and which states are always red and which states are always blue and which is which. There's some wonderful sources of data out there. I went and grabbed this file from Harvard. Harvard University Dataverse is the source of this. And it is a file of the results of every general election for the United States Senate since 1976, and again up through 2018, because the 2020 elections, which just happened, mostly haven't been certified and the data is not available yet. The nice thing is your code, when you're finished writing it, will easily be applicable to 2020. And you can just plug that in. But for now, we're doing up through 2018. So the file looks like this. Okay, I've opened this in Google Sheets. It's what's called a comma-separated value, or CSV file. I believe you've talked about this a little bit in lab. But basically, I'll show you what it looks like raw in a minute. But your first column says what year it is. The second column says what state it is, and then the third is the state post office abbreviation, the 2-letter. Remember, there's not an election in every state for the Senate every year. This year, there was not one in Maryland. We don't care about the next couple of columns. They talk about various indices and where you can look up the state office. District is always statewide. General election wasn't a special election. Candidate name, party, whether it's a write-in, how many votes the candidate got, how many total votes were cast, whether this is unofficial, and what version of the election software they use this. This is what your data file looks like. What you're going to do is read this in and go through what we care about, and all we really care about are going to be the election year, the state code. We don't care about the long state name. We'll use AZ instead of Arizona. Skip all this other stuff. Candidate name, party, and votes cast for that person, because that's really all you need to do the analysis. And because there are a ton of candidates, and with two exceptions, nobody except a Republican or a Democrat ever wins, you're going to go through and pick out only the Republicans and only the Democrats. And the two other people who do win, who you will have to care about, Bernie Sanders from Vermont and Angus King from Maine, who are officially independents, although they caucus with the Democrats. So you'll go through this. This is the data file. It's available. What it looks like if I go to PyCharm and I cat it, if you want to do this when you get the download file yourself and look at it, this goes real fast, but what it is it's just a set of rows where every value in the row is separated by this comma, and this comma is key. So that's what you're going to do. You're going to read in that data, and you're going to do some analysis. You're going to tell me which states are turning red and which states are turning blue and which states are truly purple, and do all kinds of other analysis. That's Project 3. We'll get into it some more at the end of class because I could take the whole hour and a quarter covering Project 3, and that would not do us any good because we need to cover the various sorting algorithms to get to progress. I'll come back to this later on, but that's what's out there. I do want you to make sure you can get these things up and running and installed. Again, Lab 12 is next week. So let's go to sorting and searching, and then we will come back at the end of class and talk more about Project 3. Okay. In today's lecture, we're going to exclusively use lists of integers, okay, just to make the example easier. But it all works the same. The methods we're going to talk about, the algorithms we're going to talk about, will work with sorting whole numbers. They will work with sorting lists of strings. You can actually sort multidimensional lists if you're careful and do it right, okay? As long as all elements in the list are the same type, you can sort them into an order. Now, you cannot sort an integer compared to strings, okay? You can't look at an integer and say, is an integer less than a string? That's nonsensical. But so everything in the list has to be the same type, but as long as it's all the same type, you can sort the list in any order. We're just going to use integers as our illustration. The first kind of algorithm we're going to talk about is what's called a bubble sort. Now, suppose that I have a list of integers, and I've just thrown a list with 6 elements out there that has 6 integers, 4, minus 2, 19, 944, 27, and 3. I want to sort this list so that the smallest, the most negative or least positive, as the case may be, element is first, and the largest element is last, okay? So in this case, just looking at it, I want to take this minus 2 and make it the first element, and I want to take this 944 and make it the last element. That's sorting into ascending order. Now, you could easily sort in descending order, put the largest element first and the smallest last. All you have to do is flip some greater than or equal than. It's trivial. We're going to illustrate by sorting smallest number first, largest number last. Now, in a bubble sort, what we do is we go through the list and we will bubble the largest element over to the right, to the end of the list. That is, we will compare every pair of elements, 4 and minus 2, and we will move the largest of those to the right. So we say 4 and minus 2, which is bigger? Obviously 4. So we will swap these two and say negative 2, 4, 19. Okay. Now we would have 4 and 19. And we would say, okay, well, which of those two is larger? Obviously 19. We would keep it the way it is. So we'd have negative 2, 4, 19. 19, 944. 944 is largest. Now, 944, 27. 944 is bigger. We would have to swap these two. And so therefore, we'd move this over to the right. And then we have 944 and 3. and then we would move 944 to the right. And now we have 944 as the largest element. We're going to go through the list and compare each pair of numbers. If the first is bigger than the second, swap them. And when we've gone through the list, we will have bubbled the largest element to the end. So the first time through this list running bubble sort, what will happen is the largest element will be in the right. That's the only thing I'm going to know for sure, but I will know the largest element's in the right. Now what I'll do is I'll run the bubble sort algorithm again on everything except that last element, and that'll move the second largest element to the next to last. Okay, so this is what I was talking about: -2, 4, 19, 944, 27, 3. I swap the 944 and the 27. Then I swap the 944 and the 3. And then when I run the algorithm again, I swap the 27 to the 3, and I have it as the next largest number. So now, after running the algorithm once, I have this. After I run the algorithm a second time, I'm going to have this, okay, because I'm going to compare -2 and 4. I'm going to compare 4 and 19. I'm going to compare 19 and 27. I'm going to compare 27, 3, swap. Second time through, I've got this. Then they'll run it again and so on. Now, we'll write some code and run it and show you and hopefully illustrate this, that what we're doing is we're bubbling the largest element to the right to the end of the list every time. We could do this as either iterative or recursive. And so what I've done is I've written an iterative bubble sort routine that goes through the list one by one and swaps them out. Now, let me go to PyCharm. I haven't posted this. This is the code for today. I've got all these routines that I'm going to go through in this, and it'll be posted on GitHub when we're done, along with the other code I'm going to add. Here is the iterative bubble sort routine. Start at the end at 0, and go down at 1. What this is going to do is this line of code is going to make me start at the largest element, or make me ensure that the largest element is last, and then I'm going to leave it alone. I'm going to move through. Okay. Then inside that, I'm just going to go through and swap the numbers if I need to, and then I'm going to print them. Now, I'm going to add a print statement that is going to, and this is just an interesting thing. I just noticed that my return statement is in the wrong place, which is not good, because that's going to there we go. That's going to give me the wrong value. So let's make sure it works first, and then I will. And equals the list 4, -2, 27, 19, or 944, 3, 19. Okay. New n equals iterative bubble sort of n, print new n. Okay, so let's run this. Add and see, we get the answer -2, 3, 4, 19, 27, 944. So my algorithm actually works. That's just a quick test. Let's go through and be more useful about this in terms of teaching you what's going on. What I'm going to do is I'm going to come back and I'm going to print numbers at each step. So I'm going to stay in a Python console, and I'll just put in this code. And I'll put in my main program. And now what we see is we started with this as the original list. This is the original list, or this was the list the first time through. This was the original list. And because of where I put the print statement, this is the result the first time through. The first time through, I swapped the -2 and the 4. The 27 stayed where it is. The 944 and the 3 were swapped. The 19 and the 3 were swapped. So after one time through the loop, I have indeed the largest value at 944 at the end. The second time through, and that's the 4i. Okay, so the second time through the loop, this first 4j, this first time through the loop, produced this result. And it gave me this. Now, the second time through the loop, second time through my outer loop with I, the second time through this loop, my step was -1. Okay, so I went down, and now I'm going to not the at last place, but the next to last. This step of -1 and the J loop running to I, the result of that is I will no longer consider the last element of the list. Okay, not doing a good job explaining it. Let's try again. This ensures, since I know the last element of the list is now the biggest, I don't want to go through that anymore. So that's why I'm going to the -1, and that's why I started at the end, going to the -1. This tells me to stop. This tells me where to stop. So this one says, now the second time through the loop, do your swaps, but do not bother checking that last one because we don't need to. It's done. So the second time through the loop, -2 and 4, no need to swap. 4 and 27, no need to swap. 27 and 3, swap the 3. 3, 27. 27, 19, swap. And so this is what I get at the second time through the loop. The second time through my loop, I now have this as the result of my print statement. And I know that the largest two values are at the end of the loop list. The next time through the loop, I can leave the 27 and the 944 alone, and I'm only sorting these 4 numbers. Okay. And so when I do that, I swap the 3 and the 4 and I get this. And then I run through again and I don't swap anything. And this just continues on till everything is sorted. Okay. And you can see that with this particular input, there's a whole bunch of things where nothing gets swapped, but that's okay. The algorithm works. That is an iterative version of bubble sort. I have given you a recursive version as well. We're not going to spend a lot of time talking about recursive bubble sort. You should know that it is possible to write it. You have the code for it, so you could do a recursive bubble sort if you want to. The only thing interesting is at the base case is it's a list of one number long. If the list is one number long, it is a sorted list by definition. Otherwise, I'm in the recursive case, and I just keep calling the function recursively until I get down to a list of one. Okay, so this is my recursive case down here. My base case is simply if the list is one number long. That's bubble sort. So bubble sort means that each pass through the list, we bubble the largest element to the right. When we end that pass, the largest element left, the largest element remaining is in the rightmost column. It's in the biggest element in the list, the last element of the list. Then we do that again for the next one. Okay. And so we can do it iteratively or recursively. but that's how we bubble sort. Now, bubble sort's an interesting algorithm because it's easy to understand, but it's not very efficient. It can take us a long time. One of the things we can do with bubble sort that is an advantage is stopping it. Now, in the example I gave you in PyCharm, you'll notice that the last few times through the loop, nothing changed. This list was already sorted back here. But we had to continue running through the loop to ensure that we checked everything. So the result was we did a whole lot of extra work. We did 3 extra loops through the list when we didn't accomplish anything. Bubble sort has this nice property that if there are no swaps made during a pass, we can declare the list to already be sorted. Think about why? Because if nothing is swapped, then everything is in order properly then. We're already done. We don't have to do this. And so my code that I gave you continues through even after the list is sorted. If we change the outer for loop into a while loop with a Boolean flag, then what we could do is stop the loop, change. So what I'm going to do, I'm making no sense with this. Let me try this again. What we're going to do now with this iterative bubble sort is we're going to call it efficient iterative bubble sort. I'm going to say, I'm going to define a Boolean variable called swapped. And I'm going to set it to false. Or I'm sorry. I'm going to call it no swaps. I'm going to set it equal to false. And I'm going to make this a while loop. Let me fix this. Instead of a for loop, you know what? I'm running way behind. We will cover the efficient iterative bubble sort on Wednesday. I apologize for that. I want to get through the other things and have time to talk about Project 3. So we'll get to that on how you can stop it early. The point is that if the list is already sorted, you don't have to run all the way through. What you can do is decide there have been no swaps made in a loop, in an iteration, and then you don't have to run anymore. That's bubble sort. Okay, bubble sort, you're comparing every 2 numbers and swapping them. Selection sort is a little different. We're going to search through the entire list to find the smallest element, and then we're going to swap it with the first element in the list. Now, this one, it's hokey, I apologize, but there's a video that might help illustrate this on YouTube. So hang on a second. That's fine, the right thing. I don't want the 3-minute, I want the 1-minute version. Here we go. Okay, we will ignore the code because the code it's going to show you is in a different language. It's not in Python. It's in C++, but the key is how this works. Okay, first step, select the lowest element in the array that's left, make it the smarting position, and then you have to do something with the other ones. So here is our unsorted array, 64, 25, 12, 22, and 11. And we want to sort this array the same way we did with bubble sort, so that the largest element, the 64, is in the right, and the smallest element, which in this case is going to be 11, is going to be in the left, and everything else will be sorted. So what we're going to do is we have to go all the way through the list. We're going to look at each value in the list, and we're going to identify the largest. Okay, so that's what's going to happen. Okay, 64, 25, no, 64 is still biggest. 12, no, 64 is still biggest. 22, no, 64 is still biggest. 11. Okay, so we have to swap 64 and 11, and now we have the largest element to the right. Okay, now we have to go through the list considering just these four, considering the 11, the 25, the 12, and the 22. And what we're going to do is we're going to go through, and we don't have to worry about the 64. Okay. And now we found that the array is sorted. Again, we have to check as to which of these is biggest. So selection sort, we're going to go through, like I said, the code is not in Python, it's in C++, we'll ignore that. That's the idea of a selection sort. Pick the biggest element and make it the last. Pick the smallest element, make it the first, either way. The video actually picked the smallest element and made it first. It's the same idea. We'll pick the biggest element and we'll move it. And I'm looking at the code. Okay, it looks like the code I did actually synced with that video. So let me reset. We went through, we found the smallest element, and we made it first. Then we went through the rest of the list, made the smallest element, made that second, and repeat until the list is sorted. Because we select the smallest element, this is called the selection sort algorithm. Okay, it looks like this. Here's my original list. I go through 4, -2, 19, 944, 27, 3. Which of those is the smallest? Well, -2 is smallest. So I swap -2 with the first element of the list. And so now I have -2, 14, 4, 19, 944, 27, and 3. Now, I can ignore the -2. I know it's the smallest element in the list, and we're good. I have to go through the remaining, and I have to select the smallest element in the list. 4, 19, 944, 27, and 3. 3 is the smallest element. I swap with the first. I swap the 3 and the 4, and I get this part, and I've still got these that haven't changed. Now I have to go through these 4 elements, 19, 944, 27, and 4. The smallest element there is 4, so I make that the next element in the array and shove it, swap with the 19. Don't bother touching the 944 and 27. Okay. Now the 944, 27, 19. 944 is biggest. I swap it with the 19. Or 19 is the smallest, move the 19 here, now have 19, 27, 944. Okay, so remembering my algorithm, I am selecting the smallest. So here I selected the smallest, it was -2, I made it first. I selected the smallest remaining, it was 4, or 3 rather, 3 is smaller, I made it the second element. I went through here, the smallest is 4, I put it here. I went through the remaining. 19 is the smallest. I put it here. Now I would go through again and decide which is the smallest out of 27 and 944, and 27 is the smallest. Iterative. You could do it iteratively. You could do it Recursively, here is the iterative code. The iterative code starts with, let's find the smallest item in the list. This is an algorithm for finding the smallest algorithm in the list. Smallest equals I. Go through and say if anything else is smaller, smallest to J. So what I'm doing is I'm saying the first item in the list, I'm going to start with that being the smallest. If I find anything smaller, then I'll keep that as the smallest. The reason I start with the smallest item in the list rather than 0 is it may be all negative numbers. Okay, so that this code right here tells me which is the smallest element. And now when that's done, I know what the smallest is. And now I just have to swap it with the first element. And that's this. So that is the iterative selection sort. And if I go back to Python, to PyCharm, I have my iterative selection sort. Here is my loop that finds the smallest element in the list. As we've said, this is the loop that finds the smallest element in the list. This is the code that swaps that smallest element with the first element in the list. And now I've done, and I have to put the whole thing in a loop, a for loop, to go through and make sure I do this with all the numbers. One time through the list gets me the smallest element first. Then I continue through the loop to get the next smallest element second, the next smallest element third, and so on. That's the iterative version of this loop. There is a recursive version. The recursive version is fairly straightforward. The base case, again, a list of one element, by definition, has to be sorted. And so my recursive case is I still have to find the smallest number. I find the smallest number, and then I swap it. And now I can call recursively with the shorter list. So the iterative version, I ran through an outer for loop. The recursive version, I just called myself my function recursively with a shorter list. Okay, and then I returned everything when I put it together. Selection sort does not have the advantage of, this is the code with the recursive sort as well. Selection sort does not have the advantage of bubble sort in that I cannot cut the algorithm short. I cannot stop the algorithm early. Even if my entire list is properly sorted without swapping anything, selection sort is going to run all the way through every time, just the way the algorithm works. The bubble sort efficiency of being able to stop if there's no swaps does not apply. I can't do that. So that is the selection sort. Now, there is one other algorithm we have to study. It's an important one. It'll be crucial for you going forward in computer science because it's the most efficient algorithm, and it's called quicksort. And it's called quicksort because it's very quick on average. It is the most efficient algorithm. Now, what we're going to do on this video, skip the ads. I'd ask UMBC to pay for the non-link version. Okay. What quicksort is going to do is it splits the list up. We select an element called the pivot. That is any element in the list. We just pick one. In this video, they're going to pick the last element in the list as the pivot. You could pick one at random. You could pick the first. You could pick the last. I'll look at the algorithm version I gave you. I believe I also picked the last as the pivot. It really doesn't matter. Just pick one. Okay. We call that pivot element, and we're going to split the list, the array, around it. We're going to pick that element, and then we're going to set up the list so that everything smaller than the pivot is to the left side, is before the pivot value, and everything bigger is to the right. So pick a pivot value, then rearrange the list so that everything bigger is to the left is before, everything smaller, or I'm sorry, everything smaller is before, everything bigger is after. Okay, so let's let the algorithm run through. Then we're going to recursively go through and do that again, and I'll stop the video when we get to that point. As I said in this video, they picked the pivot as the last element. Okay, the last element is 70, so they're going to pick the 70, and what they're going to do is they're going to write code so that everything smaller than 70 is going to be over here on the left, everything bigger than 70 is going to be on the right, and the 70 will be in the proper place. Now, I didn't say that those things to the left of the pivot are going to be in the right order. They're probably not. They're probably not going to be in the right order, but they'll be to the left of the pivot value. Okay. So we're going to go through. 70 is the pivot, and we're going to check each value. And if it's less than 70, it'll stay on the left. And if it's bigger than 70, we'll move it to the right. Ignore the code again. This is C++. There were no good videos of Python code that explain this. Okay, so here we go. Come on, move it. Okay. We know that the 80 and the 90 are going to have to move over past the pivot. Okay. We know that the 40 is going to be before. So since we know the 80 is bigger than the pivot, it's going to have to go to the right. We're moving things to the right is what's happening here. This set of swaps you're seeing here, what it's going to do is it's going to make sure that the 70 winds up in the right place with everything bigger to the right and everything smaller to the left. Okay, now, you stop this here. The only thing that was done was the 70, the pivot, was put in the right place. It's in the proper place in the array, in the list. Okay? That's all we've done is one step. Now, it just so happens from looking at them that the 10, 30, 40, 50 are in the right place, but we don't know that. We don't have any guarantee of that. Okay? So what we're going to do is we're going to recursively call quicksort on this left side, 10, 30, 40, 50. And then we're going to recursively call quicksort on the right side. And when it returns, then we will have a completely sorted list. So the 70 is in the right place. We're going to call quicksort on 10, 30, 40, 50. It turns out to be a very boring thing to watch because everything's already in the right place. Pick the pivot, which is 50. Go through it. Everything is to the left of 50, so we're done sorting. Now we recursively call quicksort on the right. That's the 80 and the 90. The 80 is the pivot. We do have to switch the 80 and the 90. And now that returns. So the list is sorted because we started by putting the 70 in its proper place with everything smaller to the left, everything bigger to the right. Then we recursively called the quicksort algorithm. Okay, so the idea here, pick an element, call the pivot, sort the list so that everything less is before, to the left, if you will, everything that's greater to the right is after. There's no guarantee they're going to be in order. In that example, that was probably a bad video to show, because it just so happened that the stuff on the left was in the proper order. May or may not happen. You have to recursively call the quick sort routine. We're going to go into detail on Wednesday, but for today, what you need to know is quick sort, on average, in almost every case, is way faster than bubble sort. It's way faster than selection sort. Okay? That's why it's an important algorithm. In practice, essentially, nobody uses bubble sort and nobody uses selection sort because they're slow. It's good to understand them. It's good to understand how they work. Quick sort is the thing that people use because it's very, very fast, and that's, part of Wednesday's lecture to get into detail. Okay, so here's another example before we get into the code. Just checking my time here. Again, we have this list 4, -2, 19, 24, or 944, 27, 3. Okay. In this case, I guess I picked the first value walking through this as the pivot. In the video, they picked the last value, and doesn't matter. Pick the middle value, doesn't matter. I picked the first value as the pivot, and I said, what's less than 4 and what's greater than 4? And I went through the entire list, and the things that are less than 4 are -2 and 3. And the things that are greater than 4 are 19, 944, and 27. So now I call quick sort on -2 and 3. Pick a pivot. Let me be consistent with what I have been doing. Let the first value be the pivot. The pivot is -2. Well, -2 and 3 are properly sorted. So my recursive call to the left side, to the less, works. Now I have to recursively call quick sort on the values that are greater than my original pivot, which is 944 and 27. Pick my first value as the pivot, 19. Everything stays to the right. Call quick sort recursively on these two, and I wind up with a sorted list. So that's what I'm doing. I'm picking a pivot. I'm arranging everything less, everything greater. And then I'm recursively calling quick sort. You can, of course, do this as an iterative function. We've said before, and if it can be done recursively, it can be done iteratively. Okay. You don't want to do this iteratively. You can look at the code. It's kind of nasty. And to me, this just makes more sense recursively, so I've just given you the recursive code for quick sort. Okay, here it is, our base case. Our base case says if we have a list of one number, or 0, if for some reason somebody started with an empty list, that is a sorted list. A list of length 1 is sorted. That's our base case. What's our recursive case? Our recursive case, pick a pivot. Here shows what I did on the previous slide. I picked the first element in the list as a pivot. In the video, again, they picked the last. No big deal. Now, rather than swap elements in the individual list, because lists are mutable in Python, what I did was I started with 3 entirely new lists. I had 3 new lists, and everything that's less than the pivot is going to go in the less list. Everything that's greater than the pivot is going to go into the greater list, and everything that's equal to the pivot, because I may have several entries with the same value, that's equal to the pivot is going to go in this list. So by using 3 brand new lists, I avoided the direct swaps. In the video, they made direct swaps of things in the array and the list. I don't want to do that. I'm going to start with 3 entirely new lists. That makes it easier to me to call the recursive function. So I know that I've got a list of at least 2 numbers. I know that the list of num sub 0 is my pivot. And now I've got these 3 empty lists to work with, less, equal, or greater. Now what I'm going to do is I'm going to go through and I'm going to take all the elements out of the list that I called with, and I'm either going to put them in less, greater, or equal. I'm going to go through my list one at a time for I in the range. If that element is greater than pivot, I'm going to append it to my greater list. If it's equal to pivot, I'm going to append it to my equal list. And otherwise, well, if it's not greater and it's not equal, it must be less. So I'm just going to append it to my less list. So now when this loop is done, and we'll go to PyCharm in a minute, when this loop is done, I now have everything that was in my original lists is either in less, equal, or greater. Now I don't have to call quick sort on equal. Equal is just equal. 4, 4, 4, 4, 4, doesn't matter the order. What I'm going to do is I'm going to call quick sort on less, quick sort on greater, take those results and put the list together by saying, take this list, add it, concatenate it to this list, concatenate it to this list, and now this is how I'm going to get a sorted list. So that is how my quick sort is going to work. Okay, and so when we get to the code, this is what we've got. Okay, so I'm going to instrument this a little bit. I'm going to put some print statements in it. Again, this is my base case. A list of length 1 is automatically sorted. If this is more than 1, I'm going to start by this. This needs to be indented. 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 All right. I am still not lined up with my indentation. That will work. And that should work. Okay. And hopefully I don't get an error from this for not having indentations properly, but we'll find out. So this is my quick sort. Let's go down to a Python console. Okay. Now, let's just print quick sort of the list 9, 4, -2, 5, 3, 8, 5. Yeah. Okay. Okay. All right. That should not have happened. Let's see. Okay. Results is quick sort. Let's see. Try this again. There we go. That's what happens when you don't indent properly in Python. It bites you every time. Okay, so this is the proof that quicksort works. Well, how does it work? Let's instrument with some print statements. I don't want to mess up the original. So what I'm going to do is I'm going to say, okay, print less. All right. That's a new version. Now let's reload our original N. And now let's print. Okay. And now what we can see is that as we walked through this, we started out putting elements in the list, and we built what was in the pivot, and we built a list of what's less, 4, negative 2, 5, and 3, and then greater came out, and then we built the less list. And so as we went through, this is not as useful as I had hoped it would be. It basically went through and said, okay, the initial pivot was 9. Everything was less than 9. So that was why less had everything and equal did not, and greater did not. Then the next time through, the pivot was 4 when we called it on the less. And so that gave me the negative 2 and the 3 on one side and the 5s and the 8 on the other. And then we went through the various other pivots. So I've come up with a way to illustrate that. But the bottom line here is this is a recursive function that you split the thing up. You split the algorithm, you split the list up. And then you recursively call it on the smaller and the greater. And in general, it turns out to be more efficient. And we will get into that on Wednesday when we do the analysis of algorithms on why. For now, understand the algorithms. I've given the code to you. And you will use quicksort and also, I think, selection sort on project 3. But again, you could use the code I've given. It won't work exactly. You have to change 1 or 2 things, but I've basically given it to you to illustrate how these things work. You should know what the algorithms are, and on Wednesday, you'll get a better understanding of which is faster and more efficient, and which is not. Why you sort things is typically so you can find things quickly. You search very fast. You want to search and find something very fast. The default searching algorithm for any language, Python in particular, is called linear. I want to find out if a value is in a list. Okay. Did anybody get a perfect score of 75 on the exam? I have to go through every possible exam score one at a time from first to last and return a failure if I never find it. No, nobody got a 75, or I stop and return the right element when I've found what I'm looking for. Okay. And so if you picture, a book, and is the word, is the word Senate in this book? If the book's not organized in any way, then you have to do a linear search. You would look at every word in the book and stop when you either hit Senate or when you hit the end of the book and you return failure. That's a linear search. We are looking at each word, each number, each value one at a time, stopping when we find it, or going all the way through and returning failure. It will work. That algorithm will work correctly, but it's very inefficiently. If the list is already sorted, this is why sorting algorithms are important. If the list is already sorted, we can search much more efficiently. If this is like the paper dictionary and I tell you to look up Senate in the dictionary, you know how to find the S's. You're not going to start at A and look at the definition of the word A as an article in the English language and read through until you hit Senate. You're going to go toward someplace that's much more efficient. Now, algorithmically, what we use is called a binary search. The computer doesn't have the smarts of you and go straight to the S. You go to the middle of the list. So if you're going to search for something and your list is sorted, the numbers are in order, the words are like a paper dictionary, not Python dictionary, go to the middle element of the list. List, length of the list, integer divide by 2. Okay, we don't care about fractions. Take the length of the list, integer divide by 2. Compare it to the element we're looking for. Is this the word Senate? If it's a match, we can stop right there. How about that? We got a hit on the first time, we're done. Probably not going to be a hit on the first time. That's okay. If look to see if this element is greater than or less than. It comes before or after the element we're actually looking for. Okay, halfway through the dictionary, you're probably going to be in the M's. So let's say the word you find is main, as in principal, the main course you're taking, the main course for dinner, the main whatever. Okay, does that come before or after the word we're looking for, Senate? In this case, it comes before. So we will now just look at the second half of the dictionary. I can ignore everything in the dictionary before main. I can ignore everything that came before the midpoint. Now, what we're going to do is we're going to look at the part of the dictionary that comes from main to, quite often, dictionaries end with the word Zymurgy, Z-Y-M-U-R-G-Y. Okay, I'm going to look at everything between main and Zymurgy. I don't want to look one word at a time. I will split the difference and I will go halfway in between. Well, what's halfway between M and Z? It's probably going to be in the S's, but I don't want to make this too obvious. So let's say the midway word between main and Zymurgy is south. Okay. Is that the word we're looking for? Senate? No. Does that come before or after Senate in the list? It comes after. So now all I have to do, I can throw away everything after south, and now I only have to look at the dictionary from main to south. So therefore, I will just look in between. Okay. Now I'm going to see that this looks recursive. I'm just going to take half of my list, the proper half of the list, and recursively call my binary search algorithms. Okay. And I'm going to narrow down to smaller and smaller chunks of the dictionary until I hit the word I'm looking for, Senate, or until I determine that Senate is simply not there. Okay. So if you go back to your math and you look at the logarithm base 2, okay, when we talk about any quantity, we can talk about logarithms and exponents, which are opposites. Exponent is how many times I have to raise something to a power to get what I'm looking for. Logarithm is how many times you have raised it. Okay, so I'm going to take the base 2 logarithm of the length of the list, and on average, I'm going to find what I'm looking for in that many operations. If I have a list with 10 items in it, I'm going to either find that the item is not there, or I'm going to find it in 3 operations. In 3 looks, I'm going to find it. Okay, using a binary search. That's much better than searching one item at a time. Because even taking probabilistic, if I search for an item, something in a list of 10, on average, I'm going to find it halfway through, 5 times. I'm going to have to look at 5 items for a list of 10 to get it roughly on average. With a binary search, I'm going to get it in 3. That's faster, that's more efficient. So if the list is sorted, Binary search is faster. So that's why we care about sorting lists in Python, because it makes another operation, searching, faster. Now, if I'm not searching, I'm not sorting, it doesn't matter. But a lot of times these happen. These are very common operations in computer science. So we want to be able to sort a list fast into ascending or descending order so that we can then find what we're looking for or determine it's not there very fast. And binary search operates much faster than the linear search of looking one word at a time. Okay. The code is here. I've given you the recursive algorithm. There are two base cases, right? There are two base cases. If this list is of length 0 or 1, I'm going to return an error. I'm going to return a -1. That's an error that says I didn't find it. Okay? If this list is 0 or 1 long, I didn't find it. Okay? Remember that if it's a one-item list, length of 1 integer divide 2 is 0 because we throw away the remainder. So 1 integer divide 2 is 0. And so that's this base case. The list is 0 or 1 item long. My other base case is I found it. I found the target. The target is what I'm looking for. If I found the target in the list, by pure luck, I return the index. I'm returning the index of where in the list I found it. I'm returning, I found this at list item sub 10 or list item sub 1000. Okay. So I'm returning the index of where I found it. Here, I'm returning -1. There is no list element -1. Yeah, it's the last one. It's letting me know I didn't find it. This is my error. So base case 1, list is too short. I didn't find it. Base case 2, I found it. Wave the flag, return this value. Recursive cases, there are 2 of them. I haven't found it, and it's not a 0-length list. So now I just have to decide whether my target is greater than or less than the midpoint of the list. And so I'm going to recursively call with this side, or I'm going to recursively call with this side. I'm making the problem smaller. Recursion is good for this because I'm now calling with a much shorter list. And so this is the binary search code. Okay. And so what you need to know about binary search is that is a much faster way of determining whether the element you're looking for is in the list or not. It is much more efficient than the linear search, but it requires that the list you're operating on be sorted. The list must first be sorted before binary search will work. Fortunately, again, in computer science, it's a very common problem to have. And so we study these algorithms. And on Wednesday, we'll go into the performance. I'll talk more about what log means, log of n means versus n squared and what have you. For tonight's lecture, what you need to take away, and I've left myself about 10 minutes to talk about the project. So I kind of rushed through. We'll get through it again on Wednesday. What we've done is we've talked about how you sort lists into order, ascending or descending. We did ascending order in all our examples. Descending just flips the less to greater and fine. Why you sort is so you can do fast search, so you can find an item in a list. What we've talked about in terms of sorting, we talked about bubble sort, iterative, and recursive. Bubble sort means you bubble, but you compare every pair of elements and you bubble the largest element to the right every time until you're done. We talked about selection sort, Selection sort says we go through and we find the smallest element. And when we found the smallest element, we swap it over and put it as the first item in our list. And then we go back again with the rest of the list. And then the third algorithm we talked about in addition to bubble and selection sort is quick sort. We talked about quick sort being called quick because it's the best performing on average. We talked about it can be done iteratively, but you will almost always do quick sort recursively because it's natural to simply call the algorithm with the smaller list. Quick sort says you pick a pivot. The video used the last element. My algorithm here, my code uses the first element. That's your pivot. You reorganize the list so that everything lower than your pivot is to the left. Everything greater is to the right. Everything that's equal, doesn't matter, can stay where it is. My algorithm, as I said, as I showed you, uses 3 new lists rather than trying to reorganize everything in place. I don't want to swap elements in place. I use 3 new lists to build the less, equal, and greater. And then I recursively call on less. I recursively call on greater, and we're done. The recursive algorithm, the base case is this thing is a 1-item list, and then we're done. Otherwise, it's the recursive case, and we go through, and as I said, with Python, we did a list manipulation to create this sorting algorithm. After sorting, we talked about searching, 2 ways to find data, whether an item's in a list or not. Linear, you check one at a time. You start at the first or start at the last, and then you check each element till you're done. It works. It's not efficient. If the data is sorted, if the list is sorted, then you can use a binary search, which is much faster, and that's one of the reasons you use it. So that is the computer sciencey part of today's lecture, where you have the different algorithms. And on Wednesday, we'll talk about specifically how fast, how efficient those algorithms are, how much they cost. And we'll talk about the general topic of any algorithm of analyzing how much it costs, where cost can be in terms of operations, in terms of memory, in terms of CPUs, in terms of money. But it's good to know how efficient something is to know whether it'll work and whether you can afford it. So that is all on that lecture. With that, I wanted to get to the project and make sure you understood it. I put it out over the weekend, sometime Saturday morning, I think. So, Project 3, you will run and get working on your own computer, whether you have a Windows box, whether you have a Mac, it doesn't matter. The tool should run. You will submit, I will provide submission instructions. You will submit the Jupyter Notebook. It's a file called whatever.ipynb. You will submit it on GL just because that's a standard way to submit. So you will have to use Secure Copy. You will SCP. You will run the program and you will get it working on your computer. Then you will use SCP, Secure Copy, to move it to GL and submit it, and I will provide you with the instructions. Haven't done that yet. Don't worry about it. And then we will grade it. Now, what if you have a Windows box and I want to grade it on GL, which is Linux, or on my computer, which is a Mac? Should not matter. Should not matter at all. If it runs on your computer, it runs on mine. That's the nice part about Jupyter Notebooks and Anaconda and all of these things being platform neutral. They will work on Linux, they will work on Windows, they will work on Mac. You get this working on your computer. Then you move it to GL, and then you submit it, and we will grade it. And whether we will grade it on our own computers or GL really depends on what kind of a mood I'm in. It will not matter. This is a major assignment. It's worth 200 points. It should be pretty close to 200 easy ones. Okay. Here is the biggest thing I said last week, and I want to say it again and again. If you do not have Anaconda Navigator and you do not have Jupyter Notebooks installed and working on your computer, do that immediately. If you can't get it working, let me know. Last semester was a very similar project, except as I said, they analyzed COVID cases rather than election data. The biggest problem people had was getting Jupyter to work on their computer. It's one of the reasons we're using Anaconda this semester. I had them use pip. Pip is the package installer for Python last semester. And it turned out that a lot of people with Windows boxes had big problems with pip. Anaconda is a bit more robust, so we're using that this semester, and Jupyter Notebooks. Now, when you get Jupyter Notebooks installed and running on your computer, okay, you will need to make sure that 2 modules are installed. One of those, and this is step 3 in the assignment, one of those is called Pandas, short for panel data, and Pandas should come included with Anaconda Navigator. So if you have Anaconda Navigator up and running on your computer, you should go into that environment on the left side, like I showed you last week, and you can find the Pandas module and you can make sure it's installed. Okay, make sure Pandas is installed. Now, depending on the exact version of Anaconda Navigator, you may not have to install it. It may already be installed, but if it's not, click on it. I've not seen a modern version of Anaconda Navigator that does not have Pandas. So you should be able to get that in and running easily. Okay. Plot9 is a graphing plot generating module in Python. It does not, at least as of last I checked, come by default with Anaconda Navigator. You cannot go find Plot9 in that list in the Anaconda environment. So what you're going to have to do is install it manually. That turns out to be pretty easy. Okay. I put some graphics as to what, by the way, Anaconda Navigator, Jupyter, what some of these things should look like. Okay. The way you do it, the way you install Plot9 is you go to a terminal window or a command tool, PowerShell window in Windows. Okay. You go to a terminal window on Mac. Using Windows, you've got a command tool or a PowerShell window. And at the command line, you type this, conda space install space -c space conda-forge space Plot9. And that should install it. If it does not, look at the error message it gives you. You may have to fix something on your computer. Okay. It will tell you whether it needs something or not. It will tell you whether it worked. If you're looking for documentation because you can't find it or you want to know how something works, I've given you the link to Plot9. I've also given you the link to Pandas. You can look online for documentation. Now, once you have successfully installed Conda, once you have successfully used Conda to install Plot9, you're good to go. You have all the software you need. So, from Anaconda Navigator, you create a new Jupyter notebook. You give it a title. I've given you the instructions. I've told you what buttons to click on and what to type where. Okay, if it doesn't, let me know. It'll use your default browser. If you use Chrome, if you use Safari, if you use Firefox, if you use Edge, please don't tell me you use Internet Explorer. I don't want to know about it. It'll start in your default browser. And now you have a Jupyter notebook and you can run it. Okay. Call it Project 3. Save it. Save it. It's supposed to auto-save, but yeah, you know me and auto-saves. I don't trust it. Save it. Now, start your notebook. Create a new cell. Make it a markdown cell. Now, there's a tip sheet on how exactly markdown works, and I've given you the link to it. I showed you a little bit last time. 1 hashtag or # is a heading 1, like in Word. 2 hashtags is a heading 2, like in Word, and so on. This link will give you some tips on how to make your markdown look really, really good. Put your standard stuff that you do in all your assignments, your name, your section number, fall project 3, file name. Then start putting code. I've told you to import the plot9 module and then import pandas as PD. This is fairly straightforward. You just type import plot9 and then import pandas as PD. Type those two in the cell, you're ready to go. Get the data file if you haven't already. It's the data file I showed you right here. This is a Google Sheet view of it. I showed you in PyCharm what it looks like. It's a comma-separated value file. Now you have it. You can use pandas. I will put it on GL. This GL file is not there yet. I got wrapped over the weekend. If you're interested, giving credit where credit is due, this is the original source of that data file. I got it from Harvard. Giving all academic integrity, giving credit. That's where it came from. Okay, going back to our PDF. Okay. Read it in. Now, I tell you how to read it in using pandas. I could have, last semester, I spent a lot of time teaching students how to read in CSV files. I know Jeff has. I think Tommy may or may not have taught you how to read in CSV files. But it turns out the reason we use pandas is because pandas makes it really, really, really easy to read in CSV files and do cool stuff with them. And so I've given you the command to type. This is the Python command to type to read in this data file. Just make sure it's in the right directory. If you're getting error messages, if you're getting file not found, that's because it's probably not in the right directory. So fix that. Now you've got that entire file. It's in what Pandas calls a data frame. You will need it to be in a Python 2D list. So this command right here will convert it. And now you should have a Python 2D list like you've dealt with for half the semester. And it's in the variable df. And now you can do it. Now, step 9 builds on tonight's lecture. This is not crucial to your analysis. This is crucial to proving to me that you're learning Python. I want you to sort the list into descending values by candidate votes. I want the largest value first. This is the opposite of what I did tonight, but I told you tonight the only difference is switch the less thans to the greater thans. You'll put the biggest value first instead of last. I want you to sort it by column votes. There are pre-written sort routines. Do not use them. I want you to use your own sort routine. Because I want you to do it by selection sort, and then I want you to do it by quick sort. Okay? And we're going to talk on Wednesday about how you use the built-in time functions to time it. You're going to use the built-in Python time functions. What this does is it tells you how many nanoseconds something took to do it. You're going to count the number of nanoseconds it took to sort that big honking data file using selection sort, and you're going to count the number of nanoseconds it took to sort that big honking file using quick sort, and you're going to tell me, how they compared. After you've done that computer science diversion, now you're going to get into your data analysis. I'm going to tell you I only care about certain columns and I only care about certain rows. And so you're going to write some if statements to find the rows. And within those rows, you're going to take out these columns and only these columns to care about. And now you're going to have a new two-dimensional list that has just the values you want. And now you're going to do some graphical analysis. You're going to use plot9. And plot9 is going to help you draw these graphs. And I want you to draw some lines that show how party votes are changing. I want you to do some other things that will do this, that will do some analysis and let you show you have this command of Python and the tools. Again, the reason for this assignment, this is very different. If you look at the majors on Discord, this is incredibly different from the majors assignment, which is writing code to put together a telephone switchboard. The majors are focusing right now on writing a whole bunch of integrated Python code and proving you can be a big honking software developer. You are writing a bunch of Python code, but you are showing how you can use Python code and the tools to solve a problem. Well, you may not have, Senate elections in your major, but you're using, you're using this to solve what is not necessarily a computer science project, but you're using the computer science tool to do it. So that is what Project 3 is all about. Apologize, I've already run you 5 minutes over, but please, 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 at least by Wednesday, if you don't have Anaconda Navigator and Jupyter Notebooks and Plot9 and Pandas on your computer, let me know so we can fix it. Because you do not want to come up next Thursday, the 3rd of December, the night before the program is due, going, I can't get Jupyter Notebooks to work. And that was the problem last semester. We want to fix it this week if it exists. So make sure by Wednesday, please, 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 that you have Anaconda Navigator, Jupyter Notebooks, Plot9, and Pandas working on your system. You don't have to have any other code. You have plenty of time. But I want to get those 4 things showing that you got them by Wednesday. So I'm going to take your word for it that you've got them. I'm just asking you, please, Wednesday, if you haven't got those 4 things done, let me know so we can fix it. Okay? And with that, I apologize for running you so much time over. Thank you for staying with me. Wednesday, I will clean up a couple of things I messed up on these algorithms, and I will talk about analysis and which one's faster and why that's important. And Wednesday, we will also have an opportunity to talk about Project 3 some more. If you have a commitment Wednesday evening, I know it's the night before Thanksgiving, that you can't get to lecture, okay, that's fine. The lecture will be recorded. It'll be put on YouTube. It's important stuff. Please make sure you watch it. See you then.